In this video, we will discuss limit, introduce the limit definition, the definition of limit. Then we will go through some examples and some actual more modified definitions, right? So let's see the definition of limit. So our setup for limit is basically we are assuming a function is good, right? So we are assuming f is function, so y equal to f of x is always our function, right? And we are assuming that f here is well-defined, right? Domain contains this part defined around A, right? This function is defined around A, right? Here we need to know that. So we f of A here, the function value at A may not exist, right? So you have a function, you have a point, and the function is defined near A, right? As long as x is close to A but not equal to A, this function is always well-defined, right? F of x is known, is a number, right? We know that, but f of A may not exist. So we say that, this is our definition. We say that f of x goes to L as x goes to A, right? So this is one way to say the limit of f of x equal to L as x goes to A, right? Another way is a better way in many situations is a limit of f of x as x goes to A equal to A, right? It's two notations are same. So this notation are same. This both means the limit of such a function equal to L as x goes to A, right? Is what's the definition here, right? If we can make our function value f of x arbitrarily close to L, right? By what? Through a way, right? By restricting x to be sufficiently close to A, but because f of A may not exist, right? But not equal to A, right? Not equal to A, because if you plug in A, the function value may not exist, right? So let's see that. Let's see some pictures to see what's going on here, right? So let's see a few pictures. First example, if you have a function like this is what happens in many situations. So this is our x-axis, y-axis, right? We have a value A here, right? We have a limit L here. The function might behave something like this. Right? You can see that on the left side, function getting closer and closer to L as x goes to A. And on the right side, same thing happens, right? So that's our function, y equal to f of x. So function value at A here might be here, f of A, right? So the limit may not be the function value. So this picture says as x goes to A here, f of x equal to the limit, right? If you look at the green curve, it's getting closer and closer to L. So this equal to L, but for sure this is different from our function value at A here, right? On both sides, right? So you can see that this is in many situations, this is what we are doing, right? And but sometimes they could be same. Right? If you look at this new picture here, this is our second picture here. And so if you look at this is our x, y axis. So this is our a here. Your function is very nice. Right? So this is our y equal to f of x. So this is our point, right? You can see that in this case, on the left side of a, right side of a, function value both goes to L, right? As x goes to a here, f of x also equal to L, but for sure it's equal to f of a, right? So this is um, uh, right, two examples. See, under some situations, right, the function value getting closer and closer to the limit, but this limit may not or could be the function value at a, right? Sometimes f of a may not even exist, right? Okay, now let's see another modification of limits, because we consider both sides of a, right? But sometimes maybe on one side, the function goes to a number. On the other side, the function goes to a different number, right? Let's see a third example here. So let's see this. Let's use our, right. This is our y-axis. This is our x-axis. Let's try to write down the formula for our function. This is coming from Heaviside function, h of t equal to 0, t here less than 0, 1, t greater equal to 0, right? So if you try to sketch this function on the right side of 0, the function is always 1. So this is 1 here. This is a solid because h of 0 equal to 1, right? So this function look like this on the right side, and function look like this on the left side. Right. Now you can see that if a here is greater than 0, so function value is always 1, right? Fix your a no matter where on the right side, right? Even very close to 0, right? As long as near that number, this function value is defined, right? This is always 1. We know that as x goes to a, no, t goes to a, h of t equal to 1, right? If what happens, a here less than 0, as t here goes to a, h of t equal to 0, right? So that's the very easy observations, right? On the left side of 0, right side of 0, function value is fixed. Now, if you look at 0, right, that's something different. And now you can see that as x getting closer and closer to 1 on 0 on the as t, right? This is our t, sorry. So our variable is t, not x, right? As t goes to 0 on the t here goes to 0 on the right side. So that's a notation for t goes to 0 from the right, right? So as t goes to 0 on the right side, h of t is always equal to 1. So h of t goes to 1. As t here goes to 0 on the left side, right? This is t goes to 0 from the left. Then h of t is always 0. For sure it goes to 0, right? This goes to 0. So this limit at 0 doesn't exist, right? Because they don't go to the same place. So which means as t goes to 0, h of t does not exist, right? But by our discussion, this function has a right limit and also has a left limit. So we can write that down. So as t goes to 0 from the right side, h of t equal to 1, and as t goes to 0 left side, h of t equal to 0. So that's one way to describe what happened, right? Okay, now let's try to write down the official definition for the right limit, right-hand limit, and the left-hand limit, right? So let's write down our function, right? So y equal to f of x, and f here is defined at any x with x greater than a, right? When x is greater than a, this is defined. So we say that what we say what, right? We say the right limit, which is as x goes to a on the right side, f of x equal to L, right? So we see the difference, right? So if we can make what f of x arbitrarily close to L, right? By what? By restricting x sufficiently close to A and greater than A, right? So make sure our x value is getting closer and closer to A on the right side, right? So that's the meaning of this. So similarly, we can define as x goes to A on the left side, f of x equal to A. Just to make our function value arbitrarily close to L by restricting x sufficiently close to A here on the left side. So x goes to A here means on the right side means x is greater than A, getting closer and closer to A. X goes to A minus means x getting closer and closer to A, but x is always less than A. Right, less than A. So very important fact, right? You can see that the meaning of as x goes to A here, f of x equal to AL, then if and only if, right? So if and only if, so that equivalent, that the left limit x goes to A on the right side, f of x equal to as x goes to A on left side, f of x equal to A. So that's very important. Both limits are same, then the limit exists equal to the same number, or otherwise the limit does not exist.